All right. So any questions about the discrete time control loop? Any questions, please? Is everything clear? Let me ask some of you guys just for the confirmation. Hey, awesome. Is everything clear to you up
Yes,
to
sir.
now?
Yes, sir.
All right. Yes, Mahindaratna and Tarka?
Yes, sir.
Clear, right. Dayavan sir.
Yes, everything's clear.
Okay. Sanjeev Kant.
Yes, sir. Everything's clear.
Right, okay, good. All right, let's move on. Now, one thing we got to be very careful about is when you bring in new components to the plant, right, the loop, right, we have to check in different aspects, right, what is going to happen to the plant, right? Now, when you look at the control systems, right, one of the major concerns, right, is what's happening to the frequencies that are propagating from left hand side to the right hand side. Finally, it is the frequency response, right? If you get all of the frequencies going from left hand side to the right hand side, right, you're very happy, you're done. Then everything works exactly the way we expect. The controller works the way we expect. All the components, the actuator, the plant, everything works exactly the way we expect. This is the ideal situation, right? But the reality is far from being ideal. There are a lot of non-ideal anomalies in the blocks. If you look at these ones, controller, zero to hole, plant and actuator, right? We need to check one by one, right? What this guy is doing to the signals, right? Which are going through the block, right? I think we have done this in body. So I'm just referring to body. What is controller? What is zero to hole? What is GS? Then you can see some of these blocks, right? They allow some of the frequencies to propagate from left to right, right, without any distortion, without introducing any distortion. Then we are happy. And all of a sudden, if you figure out any of these blocks, right, slow down some of the frequencies, okay, change the phase of the frequencies, or take the energy out of some of the frequencies, then we got to be very careful, because then what we expect, right, will not be implemented there within the controller. So that's why it is extremely important that we analyze these blocks in the frequency domain and then figure out the frequencies are not distorted too much, right? Remember, this is the most important thing in control system design, that you check all of the blocks, right, operate in a healthy manner in sending the frequencies from left to the right, okay, without much distortion. So with that, we open up a discussion like digital errors. When we discretize a continuous time plan, right? Already you know this is approximate version of analog system. When you say approximate version, you communicate that there are errors. Okay, so we want to look at these errors. We don't worry too much about errors because engineering is working with errors all the time, right? If the errors are within the tolerance margin, we are happy. We don't design things to unacceptable accuracy, precision. Okay, so we just deliver, right, what is required, what is asked for, okay, what is laid down in the specification. So we try to design to meet the specification. We don't want to go beyond that, right, and design very high precision thing for what it is not asked for, right? So So it's all about engineering and all about designing things to meet the specification. So knowing the errors will help you to figure out, right, whether the errors are acceptable or not. So let's look at the zero to whole block. And of course, zero to whole has time delay, you know that. And time means phase in frequency. Because it is a rotating phasor, right? Rotating phasor, the sinusoidals, right? So if there's any time from here to here, right, it is time difference and also the phase. All right. So you can either speak in terms of time or frequency. But if you look at a very high frequency, right, same time, it rotates much more. So it's a big phase for high frequency. But for low frequency ones, it goes like that. At the same time, a very small phase. Okay. So therefore, time delay is not a big problem for slow frequencies or low frequencies. But time delay can cause significant phase loss for high frequencies. So there you can see this one is original waveform, right? And then you have these red arrows. These are the samples. And then you have these flat tops, that is the zero to hold operation. And then you have the center points of the flat tops being connected to generate the reconstructed waveform. So what you see is over here is an original analog waveform being sampled, and using the samples, the waveform is regenerated. And if you look at the two waveforms, you can see there's no significant distortion. You are happy. But one thing is really clearly noticeable, that is the offset on timeline. The reconstructed waveform is time offset by t by 2, half of the sampling interval. Okay, this is what is called the time delay. And every time you have a zero to hold in your control system, the waveforms are going to be delayed by t by 2. And that is number one error that you introduce to the plant, right? The moment you convert the continuous time into discrete time. Okay, half of the sampling error, sampling interval rather. Now, if you take that time delay t by 2, okay, and try to convert it into phase delay, as I said to you, right? If you look at the frequency, this is t by 2. What is the angle? Okay, so that is the frequency of the waveform omega times time t by 2. So this is the phase loss or phase delay. And if you want to see much more familiar way, you can convert omega into rotating frequency, right? In hertz. Omega is 2 pi f, you know that, right? F is the frequency in hertz. How many cycles per second of that frequency, right? That frequency. So it is 2 pi f times t by 2. I write it here as ts over 2. Ts means sampling interval. And then it turns into this format, pi f ts and in radians. But if you want to convert it to degrees, right, this is the most familiar format for you. 180, pi is 180. Then you have f, this is the signal frequency, and ts is 1 over fs, that is the sampling frequency. And this is the most understandable equation for phase loss or phase delay. 180 degrees and then f over fs in degrees. Okay, in degrees. Now, if you know your reference signal, which is, if I pedal back, this one RK, if you have some idea of the analog version of that, right, that those frequencies actually are propagating from left to right, and when they go through the zero to pole, this happens, right? then you can calculate for all of the frequencies f. Maybe you have all the frequencies from, let's say, nearly 0 to, say, for example, 5 hertz. Okay, so highest frequency is 5 hertz. You put 5 here and you put your sampling frequency. Maybe you're sampling at 20 hertz, 100 hertz, whatever. Put it over here and you can calculate the phase loss for the highest frequency. Okay, if that is acceptable, for example, you have a certain phase margin in the loop. That's why it is very, very important, right? You know, you have some idea of the phase margin, and this phase loss should be very small compared to that one. If you have 45-degree phase margin at the bandwidth frequency, right? Let's say bandwidth frequency is 10 hertz, and you put 10 hertz over here, and your sampling interval over here, the frequency. The phase loss for the highest frequency or bandwidth frequency should be well within the phase loss, 45 degrees. Okay. Now, if it is just 5-10 degrees, that's all right. Even 10 is not very good, because then you are losing your 45-degree phase margin into 35 degrees. Right? These are very interesting calculations you can implement here every time you convert to a controller to discrete version, right? To check that out. What is the bandwidth of the plant and what sort of phase losses are there for different frequencies? So therefore, what sort of samplers should I use, right? All these things you can actually do it very, very sensible manner, very, very sensible manner. And if you do it that way, simple set of principles, right? You can have a very good redesign, digitally redesigned plant. Now, if you look at this equation, right, you can say these things. Higher frequency components of YT undergo longer or larger phase lag, and low frequency components of YT do not experience any phase lag, right? Phase lag rather. So that is why it is very important that you make sure you're compared with your bandwidth of the plant, you have a relatively high sampling interval, right? Sorry, it's a relatively high sampling frequency rather. Okay, to make sure Fs is, let's say Fs is 10 times this one, right? Then in this particular case, right, this is 1/10 of 180. This is 18 degrees. So still you have 18-degree phase loss, right? So if you have 10 times the sampling frequency, which is 10 times the bandwidth frequency. So even 10 times is not good enough. Let's go for 15 or 20 to reduce the phase loss, right? Okay. Then there's a little exercise, class exercise. What's the maximum phase loss if a 20 hertz sample system is sampled at 120 hertz? Please do it quickly. Just 1 minute. What's the maximum phase loss if a 20 hertz system is sampled at 120 hertz? Okay, we got an answer, 30 degrees. Is that right? This is the equation. Phase loss is 180 times frequency over sampling frequency. So this F is sometimes confusing. You can use any value for F, right, which is a genuine frequency in the plant, and then calculate the phase loss for that frequency, right? When you think of a system, we are worried about the highest frequency of the system, which is 20 hertz. You put 20 over here for F and divide by 120 over here, right? So 20 over 120 is 1 over 6. 180 degrees divided by 6 is 30 degrees, correct? So you will see your 20 hertz signal, bandwidth signal, undergoes 30-degree phase loss, right? The moment you introduce the zero order hole, which is operating at 120 hertz. Now, you can convert this into a different format and say, for example, if you don't want to uh, accept any phase loss more than 6 degrees, right? What is the sampling frequency you must use? So I can ask these questions in the exam also, right? And you can have these questions if you really redesign a plan to convert it into discrete format, right? In that case, you need to figure out this Fs, 180, and F is 120 hertz, right? And calculate your Fs so that this will not be more than whatever number of degrees, let's say 6 degrees, right? You cannot accept any phase loss more than 6 degrees. That's how you do that. Then you figure out Fs. That is the sampling frequency you must use in order to not to generate any phase loss more than what is specified. Okay. So any questions about that? Phase loss due to time delay. All right. Then we'll look at what other errors are there, right? There's another one, which is quantization error. Quantization error, right? Now, so I see it this way. When you convert the continuous time signal into discrete time signal, right? So if you look at a waveform, you have two axes, x and y, right? Now, in the continuous case, both axes are continuous. So you have time, any time, right? There are no samples. So there's a signal which is defined at any time, continuous. And also y is also continuous, right? You can take any signal, any value. There's nothing that you cannot take in. Both axes are continuous. In digital or discrete time, both axes are discrete, which means this is sample, so is this. And earlier, we looked at the sample signals, time samples, right? Like that. So we don't have anything in between samples. The entire time axis is sampled. You have the samples only at the specific time stamps. What about the y-axis? Y-axis is also discretized. There are steps, right? There are steps. You can't have your signal at any height. There are levels, and you have to match your signal to one of these specified levels. Okay? So, if your signal happens to fall between two levels, defined levels, you have the choice whether to go up a little bit or go down a little bit. What we usually do is that we go to the closest one. If the signal is closer to upper one, we go up. And if the signal is closer to the lower one, lower level, we go down to that level. And every time we do that, there's a little error that we introduce. Okay. And in discrete number systems, this error is half of the step, right? So one step is like number one, for example, right? In a decimal number system, number one is the least significant bit, one. Then you have 10, you have 100 and all, right? In terms of a factor of 10, right? So if you look at binary, it's different, but whatever it is, in any number system, there's a least significant bit, right? And half of that is the error that you create when you bring the sample to the next the closest level up or down. I'm just revising this because you may have done it earlier, right? The device, right, which we use to discretize the levels, not the time, right? The levels is called the quantizer. Like the sampler samples the time axis, quantizer samples the magnitude axis, right? Magnitude axis. So to show you this numerically, we have an example here, right? Let's say I have a quantizer with, say, it can have 4 bits, 8 bits, 12 bits, and so on, right? Depending on how accurately you want to represent these values, signal values, right? So if we use a 12-bit analog to digital converter, right, with a quantizer, and actual voltage goes, let's say, from plus or minus 10 volts, right? So the actual analog signal goes plus 10 to minus 10. It's about 20-volt range. And you have to sample this or quantize this 20-volt range into a 12-bit quantizer. So when you have 12 bits, right, you can have, say, 12 zeros as the lowest, which we map onto this minus 10 volts, the lowest, right? All zeros, 12 zeros. And then you have on the other side, 12 ones. There's a maximum, 12 ones, right? And we map that into plus 10 volts. So 12 ones is plus 10 volts, 12 zeros is minus 10 volts. Okay. And then in between, we have so many levels, right? And these levels are actually mapped onto um, a signal value which is in between plus 10 and minus 10 in the proportional scale, right? So how many steps are there? 2 to the 12 minus 1, which is 4095 steps are there, right? And you have entire range 20 volts divided by 4095 is the least significant bit, that is about 4.88 millivolt. So your least significant bit is 4.88. That is from one step to the next one. So if your signal falls right in between, right, midpoint, closer to the midpoint, right, you can go down, or if it is just above the midpoint, you go up. Either way, you create maximally half of LSB error. So half of this is your error. So this error is there in every sample you take into the controller, discrete sample. Every sample has this error. So with a erroneous sample, your actuator signal, right, that you the control signal that you generate is also going to be with a little error. But the issue is, in fact, there's no big issue as long as the error is very small. Okay. So there are other errors also in the control system, like noise, friction, etc. We don't model those things, right? So this is just another error that we introduce, right? As long as it is not very significant error, system will not be destabilized, so it will not generate huge anomalies. On the other hand, when you design your controllers, you need to make it more robust, right? Just a little bit of an error should not, the control should not be fragile or very sensitive to errors and all, so that the moment you introduce an error or disturbance or whatever, system goes unstable, right? So we don't design plants like that. We want to make sure the control system has sufficient level of robustness. So with that context, having a little amount of quantization error, having a little amount of time delay, right, is acceptable. In fact, with that, we enjoy all of the other benefits going discrete, going digital, right? There are a lot of advantages that we can enjoy all of them, right, at the expense of a little time delay and little quantization error. Right, so make sure these two errors are on one on x-axis, one on y-axis. X means the time, right, time delay, and the quantization error on the vertical axis. Any questions, please? Is everything clear?
Yes, sir.
All right. All right. Right. So what's next? The next topic is the zero order hold equivalent of a continuous time system. Right. Now, when you redesign, you bring these components into the plant and you're going to change the plant a little bit. Now we want to figure out what is the new plant, right? So after adding all these things. Now, if you look at the diagram over here, you can see the discrete time reference, discrete time response, and the discrete controller, which produces UK. Now I got it right, UK, it's not FK, right? Control signal in discrete time. And then you have zero order hold, you have the plant, actuator and plant together, and then you have YT, right, analog output, and then you have the sampler and converted to discrete. Now, if you look at this red cage over here, what comes into it is UK, that is the control signal. What goes out of it is YK, the response. So the block which takes control signal from one side and gives the response signal from the other side is basically the plant and the actuator together. Now, because these signals are discrete, the whole thing which is inside the red cage is the zero order hold equivalent or discrete time equivalent of the continuous time plant. Is it? So this is the discrete time plant. So you want to analyze the properties of a plant which is discretized. You got to analyze this particular plant, the transfer function of the entire series of blocks, cascaded blocks inside the red cage. Right? You got to find that out, and after that you can analyze it and derive various decisions, the pole location, stability, etc., etc. Right? So it's going to be very useful transfer function, which is the equivalent model, discrete model of a continuous time plant. Okay, right. So to do that, we need few things, right? Again, a bit of a revision. So the discrete time transfer function, which is d z, is the z transform of the sampled pulse response. I think we saw that earlier. If you want to find out the discrete time transfer function of a plant, what you need to do is to get the z transform of the sampled pulse response. You get the pulse response, give a little pulse, right? And figure out what comes out and get the z transform of that. So how do you find out the zero order hold circuit, right? And it's a discrete time transfer function. So you have this one, you have this one, you have this one, all of these things, right? You got to convert them to equivalent z transforms, right? Transfer functions, and then add them together, multiply them together. Now, when you do that, let's say starting with the zero order hold, you got to generate this UK, right? The signal, which should be the a single pass. So if you generate a waveform like this, right, which is 1 for one sampling interval and then 0, okay, then of course this is what is the zero order hold for a pulse. So the moment you got a pulse, what does the zero order hold do? It will maintain it for one sampling interval, and after that it goes to 0. There's nothing. This is the operation of a zero order hold. we have given one pulse because we want to get the transfer function of the zero order whole. Okay. So if you want to find out the discrete time transfer function of a block, this is what you do. You give it an impulse or pulse and get the response. That's it. And for zero order whole, we know that this is the output. Pretty clear. For one pass, it gets you that level, right? Constant for one sampling interval, and then it goes to zero. That's it. Now, what is this pulse? One step. You can generate this one using these two waveforms. One waveform is the continuous time signal, step signal at 1 for all time t. And then you have another one, which is offset by one sampling interval, right? It is another step signal, but offset by one sampling interval. And if you get the difference between these two, this minus this, right, you get this one. So zero order whole response for a pulse is actually UST. This is UST. This is UST minus capital T. The same US, but shifted by one sampling interval. Okay. So if you deduct this waveform from that waveform, this is what you get. Clear? So the transfer function of the zero order whole is the Z transform of US minus UST minus T. Just that. Is that clear to everybody? Shamira, is that clear to you?
Yes. Yes, sir.
Sri Lanka?
Sir.
Hi, Vihangi? Vihangi, are you there? Vitana Siri?
Clear, sir.
Right, okay. Right. So this waveform is the pulse response of the zero order whole. And the transfer function is the Z transform of the pulse response. Right? So we got to find out the Z transform of the pulse response. So this is exactly what we are doing right now. Therefore, the unit pulse response of zero order whole circuit is this one, right? In time domain, and then this is the Laplace domain. UST is 1 over S, and UST minus T is e to the minus T is 1 over S. This is the time delay. Okay, you know, when the signal is shifted, e to the minus Ts comes up front there for of that waveform. So the Laplace transform of the response is 1 over S, 1 minus e to the minus Ts. So if you want to get the zero order whole circuit, right? The Laplace transform is this. Now, for the first time, you see that. What is the Laplace transform? What is the transfer function of a zero order whole? Just this. Just this. Okay. The transfer function of a zero order whole is just this. Now, what we want is, what is it in discrete time, right? What is it in discrete time? So the pulse response of zero order whole equivalent of PS is, right? You get the zero order whole transfer function and multiply with PS. So you have the zero order whole and the transfer function of the plant with the actuator, of course, right? You combine all of these things, right? And that is the transfer function of the zero order Hall equivalent plant. Earlier it was just PS, the plant, or I should have said GS, right? Now in front of that you have zero order Hall. The additional block, right? You have to use the transfer function of that block now, because now the plant is different. Okay, so this is the zero order Hall equivalent of the plant, 1 over S, 1 minus e to the minus ts times ps. We haven't converted it yet to the discrete time, right? This is the continuous time equivalent of the zero order Hall plant. Okay. Now, if you want to convert this into discrete time, right, you need to take the z transform of this one. 1 over s, 1 minus e to the minus t ds. So there you can see this is 1 minus z to the minus 1. This whole thing is in the z domain is 1 minus z minus 1. Then you have to take the z transform of ps over s. ps over s. The ps is actually the plant transfer function, which is over S now, right? You have to convert this whole thing into Z domain. And in front of that, you have 1 minus Z to the minus 1, this one. So that will generate your discrete time plant, which is the plant in the sense the zero order Hall equivalent. Okay, you cannot just take the plant and get the discrete version. Okay, always you're going to have digital analog to digital converter, right? So the other way around, if it is a plant, it is the digital to analog converter, which is zero order Hall here. So either first order Hall or zero order Hall or any other Halling circuit is required, right, in front of the plant, front of the plant. So with that, you modify your plant now, right, and then you take the Z transform, which will give you the discrete time transfer function of the plant. So this can be easily evaluated in MATLAB using C to D, continuous to discrete, right, command in MATLAB. Please check that out, right? You can do it yourself, C to D and zero order Hall equivalent, right? So MATLAB provides you all of these things. It's a single command. It will give you the zero order Hall discrete time transfer function. And it allows you to specify not only zero order Hall, but other methods also, right? All right, now we got a class exercise. Determine the zero order Hall equivalent of PS equals A over S plus A greater than 0. It's a simple first order plant in continuous time. And I want you to get me the zero order Hall equivalent of this plant. Okay, so we're going to take a little break, maybe about 5 minutes, 10 minutes. So please work that out, and I'll see your answers after the break. Any questions about this exercise? I want you to do it now, right? So after that, we can take a break if necessary, right? Any questions about this exercise? Anything which is not clear to you, you may ask now. All right. So this is the answer to that question. How to convert A over S plus A, this transfer function, into the zero order Hall equivalent. Okay. As we saw earlier, this is what you have to do. You divide PS, transfer function, in continuous time by another S and get the Z transform of that block. And in front of that, 1 minus Z to the minus 1. Just that. We looked at the theory before the break. Okay. Now the break, the time I gave for you to work this out. So once you substitute for PS, SOS plus A, then you can break this down into these two partial fractions and then convert them into